Welcome back. In this video, we begin our discussions on Lesson 8, which have to do with limits and continuity of multivariable functions. Recall from our study of Math 1A that all of single variable differentiation, all of Math 1A, was concerned with the forward problem of ordinary differentiation. In the forward problem, this goes back to lesson 0, we looked at the ordinary derivative operator applied to a single variable function, and this one was given, and we produced an output function which we called the derivative of capital F. Remember that in order to construct this derivative, we started with a very special idea. Before we actually looked at the derivative, we looked at secant lines through the curve, or the graph of the curve, f of x. So perhaps you have some function f, this is a general function, and you have 2 points on that curve, one point corresponding to x comma f of x, the other point corresponding to t comma f of t. And we could go ahead and label this on our graph. So here's the first point on our graph, and here is the second point on our graph. And then we drew a line through those points. We call a line going through 2 points on a graph, that's called a secant line. Because all lines have slopes, we said that we could measure the slope of the secant line through these 2 points using what we might call the slope formula, which was to say that we had the output of the second point minus the output of the first point, all divided by the input of the second point minus the first point. And then we said that this was the rise over the run. And then we did something really, really cool. We said that there is some value to finding the slope of the tangent line through this point. And in order to do that, what we're going to do is force our inputs to each other. So we'll actually force t towards x. And the way to think about this here, this was going to be t minus x. That's the rise or the run here, right? That's what's going to be on the bottom. And then this thing right here was going to be f of t minus f of x. And when we forced t to x, this thing was going to go to 0, this was going to go to some number, and the ratio of those two things would be the slope of the tangent line. In particular, we could look at transforming the secant line into the tangent line, and here's a graphical representation. And what we did in this case was we said that the slope of the tangent line at point x, we'll call it f prime of x. So this has a very special thing. The graphical representation of the derivative was the slope of the tangent line. And physicists, of course, would say, no. This is the instantaneous rate of change. And then we as mathematicians would say, yeah, you're right. And we said that, hey, this instantaneous rate of change came from taking the slope of the secant line, which we've just calculated as that value, and then doing a limiting process. And the limiting process said, translate this slope into the slope of a tangent line by forcing t towards x. Secant lines are lines through 2 points on a curve. Tangent lines are lines through 1 point on a curve. In this case, the point that this tangent line goes through is x comma f of x. So that's a quick representation of the theoretical foundation of Math 1A. And then, of course, we did a bunch of theorems on how to take this limit quickly. We looked at applications, blah, 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 blah. Once we had the concept of transforming a secant line into a tangent line, we said that that concept depended on forcing t towards x, or forcing the inputs towards each other. The way that we did that forcing was with a tool called a limit, and in Math 1A, these were single variable limits. We just saw on that last diagram that the limit showed up after we took the slope of our secant line through the 2 points on the curve. We then forced one of the points to the other point through inputs. So in this case, that of course should be an x. I did a squiggly x for some reason. And then for whatever, there we go. So this right here is called the limit definition of the derivative. In slope notation, and the reason we say slope notation is this quotient right here is the slope of a secant line. Notice this is a single variable limit. We further saw that when we were taking these limits, we could do a substitution, and we could say, let's let h be equal to the difference between t and x. So along the line, when we looked at here was x, and here was t, we said that the distance between these two, or the actual difference between the two, which is different than the distance, right? Distance is a magnitude. This is literally a signed quantity. We'll call that h. And then the moment we call that h, this means that t is equal to x plus h. And we could restate the limit definition of the derivative using this dummy variable. I hate it when people call variables dummies. That's not very nice. Where we substitute in x plus h minus f of x all divided by h. Notice this is still a slope of a secant line, and we're still forcing the distance between x and t to each other. This limit definition had a very special name. Right here, for those of you that are going to go on to classes like Math 2A, Math 2B, or any upper division classes that depend on calculus, this has a very special name, just this quotient. It's called the difference quotient. It shows up in finite element analysis, finite difference analysis. It's a very, very popular thing in future classes in math. And then this limit still is a single variable limit, of course. And we call it a single variable limit because it's limiting a single variable function. This whole thing, when we look at this entire definition, this is what we call the limit definition of the derivative in derivative notation. Notice that both of these should be ordinary derivatives, and they're ordinary because they're not very interesting. No, I'm kidding. They're ordinary because they have single variable functions, and in calculus we use this thing where anything we say single variable is ordinary. This was derivative notation because when we went to go prove theorems about derivatives, it just so happened that this form allowed us to do a lot more for a lot less work. So this definition up here allows you to see a direct connection between secant lines and limits. This definition right there, I like it when you define right there. This definition allows us to use the definition of derivative, but to use it in practice to prove theorems and make our life a lot easier. Okay, that's a lot of work. We're doing a quick recap. This is directly relevant to lesson 9, by the way. I'm setting you up. All right. So what I want to say is that there are actually two major ideas that are combined together to get the definition of the ordinary derivative. One, the first major idea before we do anything else, is the idea of this difference quotient. And the way I like to say this is, in less formal terms, this is called the slope of a secant line. We begin defining derivatives by starting with the slope of a secant line. Then we turn a secant into a tangent through a limiting process. So this is the concept of transforming secant into tangent. Since this measures slope and then we hit it with a limit, this also measures slope, and this is the slope of the tangent line. As a quick recap, let's look at each of these individually. The difference quotient f of x plus h minus f of x divided by h measures the slope of the secant line through the 2 points, x comma f of x and x plus h comma f of x plus h. Remember, the word secant means through 2 points in this context. After we finish measuring the slope of the secant line, we transform this into a slope of a tangent line through a limiting process. In other words, we force this input, x plus h, to this input, x, by letting h go to 0. When h goes to 0, it becomes x. And then we look at the ratio, the limit of this ratio, and that limit is called the derivative. In order to create derivatives, we need first a slope of a secant line, then we hit it with a limit, and we get the slope of the tangent line. Based on this idea, much of Math 1A was focused on limits because these are the formal mathematical tools that allow us to transform secant lines into tangent lines. And like all nerds, I want to say, wow, that's really powerful mathematics. In Math 1C, we are going to generalize this concept of an ordinary derivative to multivariable functions. In particular, instead of taking ordinary derivatives, we're going to take what we call partial derivatives. There are two ways to signify partial derivatives. One is with the partial operator. So partial operator kind of looks like a 2. We'll talk more about this in lesson 9. So this says partial derivative of f of x comma y. And this you could also write as f sub x of x comma y. Remember, anytime we take a derivative, we are going to need to do first first a secant line, and then transform it into a tangent line through a limiting process. So here you would say f of x comma y, and then we use dummy variables a comma b. And then on the bottom, we're going to look at the distance between a, b, and x, y. Don't worry about this. I'm just giving you an idea. So you have the change in output, and then you have a distance, the length in input. That's the slope of a secant line. And what we're going to do is, so really, I'm going to say something crazy here. When we're taking a partial derivative with respect to x, we hold the y constant, which is quite interesting. And then we take the limit as a comma y goes to x comma y. Slope of a secant line, limiting process. Don't even write this down if you don't want to. I'm not going to say this is part of lesson 8. But what I want to show you is, do you notice something special about this? Ding, 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 ding. This is multivariable limits. Lesson 8 is all about how these things work because we're going to need this when we construct partial derivatives. This is a fundamental tool in taking derivatives. So a quick recap. In order to figure out how to take partial derivatives, derivatives of multivariable functions, we need to learn how to take limits of multivariable functions. Enter lesson 8. Are you excited? I hope so. Let's go on to the next video where we start looking at multivariable limits by recalling our understanding of single variable limits. See you in the next video.